Here we're looking at another inorganic topic. We're going to look at the halogens, which is group 7. Now, you've looked at group 7 elements at GCSE. We'll look at them again here in a bit more detail. This particular lesson, though, we're going to look at the physical properties of these group 7 elements, otherwise known as the halogens. Now, the ones that we're looking at are fluorine, chlorine, bromine, and iodine. We don't really discuss astatine. The reason why we don't really discuss astatine is because it's rare and it is radioactive. Now, all of these elements here have 7 electrons in the last shell. Because they've got 7 electrons in the last shell, we need 1 more electron for a full shell. Therefore, they form diatomic molecules. Diatomic is 2 elements, 2 atoms rather, in an element chemically bonded together. Fluorine is a gas, chlorine is a gas, dense gas though. Bromine is a liquid. Bromine is only one of 2 liquid elements on the periodic table, the other one being mercury. And iodine is a solid. You do need to know that. You need to know that they're gases, that's a liquid, and that's a solid. You also need to know the appearance of these as well. So fluorine is a pale yellow gas. Chlorine is a greenish gas. It's greenish. Bromine is a red-brown liquid. And iodine is a grey solid. So they get darker and denser as they go down the group. So if we were to predict the colour of astatine, we'd probably predict it's going to be black. And if we were going to predict the density of astatine, we would predict it's denser than iodine, because the darkness and the density increases as you go down the group. So we're looking at the bond strengths now. So we have single covalent bonds between these atoms. Let's come back to fluorine. Let's do the other ones first. So you can see that the general trend is that they get weaker. Remember, these are measured in kilojoules per mole. So they get weaker as they go down that group. So these bonds are easier to break. However, there is an exception, and the exception here, which doesn't fit the trend, is fluorine. So that is weaker than it should be. And the way of explaining that is to actually draw a dot and cross diagram of fluorine. We're only going to show the outer shell electrons only. So this is untypical. This FF bond is unexpectedly weak compared to with the trend of the rest of the halogens. And that is due to the small size of the fluorine atoms. These are very small. And because they're very small, what happens is these electrons here, these non-bonding electrons, so non-bonding electrons are the ones that are not involved in chemical bonds. These are what we call bonding electrons, these 2 here, but these pairs here and here are non-bonding electrons. These non-bonding electrons, because these atoms are very small, end up being close together. So this non-bonding pair of electrons on this atom is quite close to this non-bonding pair of electrons on that atom. So they're too close. If they're too close, what happens is they repel. If they repel, what that does is that weakens this bond. If the covalent bond's weakened, bond enthalpy is much lower than expected. Okay, let's have a look at the size of these atoms now. So as we go down the group, the size increases. So down the group, the atomic radii increases. So we've looked at this before for group 2. And the reason why that is because there's more shells. Let's look at electronegativity. So remember, electronegativity is a measure of the ability of an atom to attract electrons toward itself in a covalent bond. So electronegativity is the ability of an atom to attract electrons towards itself in a covalent bond. So we know that electronegativity depends on the attraction between the nucleus and the bonding electrons in the outer shell. So this in turn depends on a couple of things. It depends on the balance between the number of protons in the nucleus, or what we call the nuclear charge, and the distance between the nucleus and those bonding electrons, plus the effective shielding on these inner electrons. So for example, if we consider what we call the hydrogen halides, so a hydrogen halide is a compound which contains hydrogen and a halide. So a halide is anything which is like F-, Cl-, Br-. So an example of a hydrogen halide, for example, HF there. So fluorine here has hardly any shells. Only has 2 shells. So here we've got a bonding pair of electrons there. Because we only have 2 shells in fluorine, that bonding pair of electrons is attracted to that fluorine quite strongly. However, if we compare that to something like HI, we have a bonding pair of electrons again. But if we look at the periodic table and we count how many shells iodine's got, so iodine is in the 1st, 2nd, 3rd, 4th, 5th period down. So it's got 5 shells. It's got lots of shells. Because it's got lots of shells, those electrons, that bonding pair of electrons, are not as attracted very strongly because you've got greater shielding and they're much further away from the nucleus. So therefore fluorine has a higher electronegativity than iodine. So the order for electronegativity, fluorine is the most electronegative, followed by chlorine, then bromine, then iodine, and then theoretically astatine. So the electronegativity decreases going down the group. It decreases because there are more shells, so therefore there's more shielding, and that bonding pair of electrons is further away, so the bonding pair of electrons is less attracted to the halide. Fluorine, in fact, is the most electronegative atom on the periodic table. Right, last little trend, we're going to look at the melting points and boiling points. We notice straight away at the start of the lesson that the first 2 are gases, bromine is a liquid, and iodine is a solid. In fact, what we find is that fluorine is a true gas, Chlorine is quite a dense gas. At low temperatures, it almost appears like a liquid on the ground. Bromine is a liquid and iodine is a solid. So the melting points and boiling points increase going down the group. So they increase going down the group. Let's have a look at why that is. And in doing that, what I'm going to do is I'm going to draw a fluorine molecule and draw an iodine molecule. So here's a tiny fluorine molecule and here's a really large iodine molecule. Let's draw another fluorine molecule next to this. Another iodine molecule next to that one. So fluorine molecules are much smaller than iodine molecules. Because they're much smaller, that van der Waals force of attraction between the molecules is much lower. So there's a weaker van der Waals force of attraction between the molecules. In fact, those van der Waals force of attraction between those two iodine molecules here are so strong, iodine is actually a solid. It's a simple covalent solid. There's not many of them at all, but iodine is such a big element. It's got so many electrons, therefore that temporary dipole-dipole, that temporary van der Waals force of attraction is really strong. And we see that in their states as well. Gas, dense gas, liquid, solid. Okay. That is the physical properties of the halogens. Quite a short one, that one.